Hi, my name's Aaron Tome, and I'm going to give you an introduction and tutorial on using the Crux tool for symbolic testing of C and Rust programs. Symbolic testing is an approach to improving software assurance that goes beyond standard unit testing by building on some of the techniques introduced in property-based testing. In particular, it takes the same sorts of property-based tests that tools like QuickCheck use, but allows you to get exhaustive coverage of the input space of your programs. And it does this by building on symbolic execution to build up a mathematical model of the behavior of your program, and then using SMT solvers to prove that the checks that you've embedded within your program always succeed. And so the rest of this talk is going to be an interactive tutorial on how to use Crux on a number of particular C and Rust examples. If we take a look at this particular function here, this implements a version of the find first set algorithm, which is available in many standard C libraries. This returns the index of the first bit in a word that is set, that is equal to 1. And so it should always return, in this case, a value between 1 and 32 for a 32-bit word. This particular implementation we have here is somewhat strange and might not be obviously correct to you. Maybe the obvious way to do it would be to loop over all of the bits and return when you find one that is set. So in this case, to determine whether this code is correct, we can write some test cases like the ones you see in the main function here. We assert that the output on a couple of particular input values is equal to a known constant. And so now if we take this program and compile it, we can run it and see that it succeeds without an assertion failure. However, doing testing this way only covers a tiny fraction of a program's input space, and so typically you might want to find some way of exploring more of it. So let's take a look at a slightly more complex version of that program, where we, instead of looking at specific outputs, we generalize this to a property of the outputs. So in this particular case, we've made something that's a little more coarse than what I had before, in which we just take the output of the FFS function and check that it's within the bounds that we expect. It returns a 32-bit integer, so it could return something far too big, and we want to check that at least it returns something that satisfies this one property. So now we can call this FFS inbound check on a couple of specific inputs, and the nice thing here is that we don't need to know what the correct output is. We just need to know that it satisfies this particular property. And so similarly to what we had before, we can compile and run this program, and it succeeds as we would expect. However, this tests even less than the first one because it just checks that these particular values are inbound, not that they are correct. So let's look at a slightly more sophisticated version of this still. So in this case, we write a different version of the FFS function that works like I described a little bit earlier. In this case, we have another FFS ref function, which iterates over all of the bits in the word and returns when it finds one that is set. So it may be easier for us to convince ourselves that this FFS ref function is correct than it would be for the FFS imp function. So just like we had for the inbounds case earlier, we can write a property that says that for a particular input value x, we want that the FFS imp function returns the same thing as the FFS ref function. So now, once we have that, we can actually check the correctness on any particular input that we like to provide. We can do these two concrete inputs, or we could do something like this other example where we iterate over a bunch of random inputs and check that it's true for all of those. So we can quickly expand the input space of programs that we can check this way. And so just to take a look at how these programs work in practice, we can run them, and they all succeed as you would expect. So now we know that there are at least 100 input values, and we don't know which ones, for which this FFS imp correct function is correct. We could run it several times if we want, and we'll see that it continues to succeed. But this still is a tiny fraction of the input space, which is 2 to the 32 specific values in this case. So we'd like something even a little bit better than that. But presumably, if you've done any testing of software in the past, these examples I'm showing right here are very straightforward, and resemble the sort of thing you might write for your own code. So now let's look at a slightly different version of that, in which we compare the implementation to the reference function just like we did before. But in this case, instead of calling FFS imp correct on a concrete value or on a random value, we call this special function crucible int32t, which is defined in this extra header file crucible.h that we included. Calling this function constructs a symbolic input value when you run this C program through Crux, rather than the concrete values that you would normally execute it on. And so when you're running it through Crux, it can do symbolic execution and track the progress of that symbolic value throughout the program. And then when it encounters a call to this check function, it emits a goal to the SMT solver that can check to see that this can never fail. So we can run Crux LLVM on this input file, and we'll see the following output. It says that it attempted to prove one goal, and it successfully proved that one goal. Therefore, the overall status of the program is valid. And now this means that FFS imp and FFS ref are equal for all 2 to the 32 possible input values. What if the program instead had a bug? So let's take a look at a different example in which we have a different FFS bug function that produces the wrong value for one specific input value and otherwise does the same thing as FFS ref. Now, if we run this program through Crux, we'll get a different output. In this case, you'll see that there were 2 total goals, one for the correct version, one for the buggy version, as we see over here, and it managed to disprove one of these. And there are 2 results that come out of this. The first is that it has produced a debug executable that calls this program with the result of crucible int32 set to the counterexample that it discovered. Now I can run the debug executable that it created, and we'll see that it did, in fact, fail an assertion on line 38. But in addition to that, we can run the same thing within a debugger. So if I load up LLDB, the LLVM debugger, on the same executable that I just ran, I can tell it to create a breakpoint on line 38, as suggested by the output of Crux. Then I can run it, and it will stop at the call to FFS bug correct. And at this point, I can poke around in the internal state of the program to determine what went wrong. For example, I can print out the value of x, and if we want to compare that to the value in the program, because it's in decimal instead of hex, we can see that if we print out that hex value, we get the same decimal value. This is one way of looking at the output of Crux LLVM. The other way is to look at a rendered HTML file that it creates. If you look at this HTML file that came out of Crux, you'll see a list of 2 goals on the left-hand side. One highlighted in green to indicate that it succeeded, and one highlighted in red to indicate that it failed. If we click on the green successful assertion, we see that it highlights the particular call to check in the program that succeeded, and that it managed to prove will always succeed. If instead we select the red failed assertion, it will highlight the associated check line in red. And in addition to that, alongside the call to the crucible int32t function, it will list the particular counterexample value that it discovered during symbolic execution that causes the assertion to fail. So far, all of the examples that we've considered have been in C, but Crux also supports analyzing programs written in Rust. If you look at the add correct concrete function here from the curve 25519 DALEC cryptographic library, it shows a correctness condition for one of the addition functions defined within the library. The scalar52 add function is an optimized implementation of a function to add 2 large integers, a and b, modulo some constant L defined within the library. This test chooses 2 specific values for a and b, calls the scalar52 add function on those 2 values, converts both of them to big integers, and calls the standard bigint library function to add those 2 numbers together, and then calculates the result modulo the value of L converted to a big int. And then it checks that the result of the scalar52 add function is equivalent to the result of the big integer addition. So this test ensures that the scalar52 add function is correct on two specific concrete values, but ideally we would like to know that it's correct on all input values. This add correct symbolic function does the same process using Crux to test on all possible inputs symbolically instead of on two concrete inputs. Notice that this particular function has a special Crux test attribute at the beginning. This tells the cargo integration for Crux that it should always evaluate this particular function as a test within Crux, similarly to how functions annotated with the test attribute work with the normal cargo test function. So let's look at the differences between this function and the previous version. Instead of constructing two concrete input values, this function calls the symbolic scalar function to construct symbolic scalar inputs for both A and B. It then uses a special large bit vector type provided by Crux to do the large word arithmetic. This produces the same output as the normal big integer library in Rust, but it does so in a way that's more efficient within Crux, and it allows the analysis to proceed more quickly. Now that we have a function annotated with the Crux test annotation, we can use cargo Crux test to evaluate it. Now, as we can see in the output from Crux, analysis of this program led to 50 total goals to be proved, and Crux managed to prove them all within a matter of about 10 seconds. So now we know that this scalar addition function is correct for all inputs, rather than those included in the unit tests packaged with the library. As a final example, I want to demonstrate how Crux can be used to do analysis of programs that make use of floating point operations. You can now see an implementation of the floor F function taken from the musl C library. This function uses a combination of shifting, masking, and arithmetic operations on integers to calculate the largest integer that is smaller than or equal to the given floating point value and returns that result as a floating point value. Because this is kind of a complicated operation, we may not trust that it's correct. One somewhat coarse specification of this function is that the result should be less than or equal to the input, and the result should be greater than or equal to the input minus 1. If we know that the result is in fact an integer, then this is sufficient to show that it's correct. We don't have anything in this check to ensure that last condition, however. You may notice one new construct showing up in this example as well. This call to the assuming function is used to state an assumption under which we want to perform our analysis. You can think of this as saying that I want to prove in all cases where this assumption is true that the property stated in the check is also true. And if the assumption is not true, it doesn't matter. This particular assumption refers to an idiosyncrasy of IEEE floating point semantics. In particular, this floor function is not correct for inputs that are not a number, or nan. And in IEEE floating point semantics, the value nan is not equal to itself. So we can rule out nans by assuming that x is equal to itself. Once we do that, we can run Crux LLVM on this example. When we do this, it collects and successfully proves 3 goals, showing that this floor function does indeed satisfy this property for all possible non-nan float inputs. There are a few features of Crux that I don't have time to go into today. To see a complete list of options, you can run the LLVM or Rust versions of Crux with the -- help flag. And because there are a lot of these options available, it's possible to run Crux on a configuration file that lists a number of saved options. Crux supports a wide variety of SMT solvers, including Boolector, CVC4, DReal, STP, Yikes, and Z3. If you think Crux sounds useful, it's freely available with an open source BSD license. You can find the source code and documentation on GitHub, and binaries are available there as well. Finally, Crux LLVM and Crux Mir are also available on Docker Hub for easy installation. Thanks for taking the time to hear about Crux, and I hope you find it useful.